Hello everyone, I am Partha Mishra. I am a sophomore student of ceramic engineering at NIT Rourkela. Today I will be discussing on the topic PZT, a smart material that produces electricity on heating. Today's outline will be, first we'll discuss about what are smart materials. Then we'll move on to discuss what are dielectric, ferroelectric and piezoelectric effects seen in some crystals. After that we will zoom in into the crystal structure of PZT. Then we will discuss the phase diagram of PZT solid solutions. After that, we will understand an important concept of electric poling action in PZT. And finally, we will conclude with some amazing applications of PZT. Hope you enjoy. Thank you. So what are smart materials? Smart materials are those that can bridge the gap between a living thing and a non-living thing on an engineering point of view. Just as we living beings could feel and react to environmental conditions such as extreme heat, smart materials based on their material configuration are capable to react to a particular environment. In fact, that's why we call them as smart or adaptive or intelligent materials. They can be transducers that convert one form of energy into another, or as electrorestrictive materials that can respond to an electric field, or magnetorestrictive materials that can respond to a magnetic field. In fact, we have furthermore materials that can respond to pressure, electricity, heat, light, or even the pH of the environment. But today we will focus on two of these smart materials, that is, the piezoelectric smart materials and electroresponsive materials, and understand their behavior. In this slide, we will try to take a step back and analyze the bigger picture as we classify materials based on electromechanical effects and show how, for example, a ferromagnetic material is capable of showing a piezoelectric response. And since there are so many materials that can fall under these categories, I'll try to stick with a particular material called a PZT, which as we can see shows all the mentioned effects. So what is a PZT? It is a polycrystalline ceramic perovskite material that shows a marked piezoelectric effect. It's a molecular compound consisting of lead, zirconium and titanium, hence the short form PZT, and has the following chemical formula as we can see. It is a lead-based perovskite. We will see this perovskite structure in the next slide when we zoom in to see the unit cell of the PZT. A PZT is also a dielectric. But what are dielectrics? Dielectrics are materials that polarize very well when an electric field is passed through them. These dielectric materials are extremely desirable in capacitors. Suppose you require a higher capacitance, then as we know that capacitance is equal to epsilon naught A by D, A being the area of the capacitor plate and D being the distance between the capacitor plate, and epsilon naught obviously the permittivity of air. So to increase the capacitance, we require a dielectric material, as introducing them in between those spaces would increase the permittivity more than that for that of the air by a factor, and it will increase it by a factor of epsilon r, which we call it the relative permittivity or the dielectric constant of the material. Over the recent years, we have encountered materials whose dielectric constants are much larger, in the range of about tens of thousands. These means we can now see a much higher polarizability in these advanced materials. For example, in PZT, the dielectric constant can be around 450, hence can polarize to much higher extent. But how do crystals such as PZT have such high polarizability? The answer is that their crystals are ferroelectric materials as well. And here's why. What are ferroelectrics? Let's see that. Ferroelectrics are dielectric materials that, although have a disordered dipole in their domains, but when we cool it below a temperature called the Curie temperature, the dipoles orient in a particular common direction, thereby inducing a spontaneous polarization in the crystal structure. And not only can we use these ferroelectric to build better capacitors, but by utilizing two important aspects, that is, the changing in the crystal structure and the state of polarization, we can make better piezoelectric materials. So let's face it, what is piezoelectric materials or what is piezoelectricity? Piezoelectricity is basically made up of two components, that is piezo, which means to press, which implies that there is a mechanical motion in response to a force being applied to the material, and electricity, which is what the material is able to produce in response to the force applied. So these materials are able to generate electricity in response to a mechanical strain. Okay. But what initiates that mechanical strain in the crystal? And how is a material able to generate electricity? Let's see that. This is the crystal structure of PZT. So ferroelectrics and PZTs, the piezoelectrics, have got this interesting perovskite structure. In this figure, we can see the crystal structure of the lead-based perovskite, having a cubic crystal system with a big lead atoms occupying all the corners, oxygen atoms on the face centers, and transition metal atoms like titanium or zirconium atoms with a large positive charge of +4 in the body center. Now you might ask, what's so special about this particular crystal structure? Well, these ferroelectric crystals evolve as a function of temperature. Above a transition temperature called the Curie temperature, Tc, the structure is a perfect cubic and completely symmetrical with no polarization at all. But if we take the crystals below the Curie temperature, these cubic structures elongate along the polarization and contracts laterally, as it can be seen. And that makes the titanium or zirconium atom off-centered and shift along the direction of the elongation. And since the relative position changes, we are left with a net positive and net negative in the crystal, which has now turned into a tetragonal shaped crystal system. This polarization is brought about almost spontaneously, as there is a shift in the atoms. The other atoms also undergo a shift, and hence they also contribute to opposite charges getting formed. But since the charge of titanium or zirconium ions are much higher and can move much to a greater distance, hence they affect the formula that we can see in P equal to Q dot D. And this kind of coupling between the electrical and mechanical phenomena is one of the key cause of piezoelectric effects in such materials. As we saw that when we apply an electric field to a piezoelectric material, it causes the crystal structure to distort and all of its polarizability increases. So the dielectric constant and the piezoelectric coefficient goes up. Now let us take this step further and understand what's going on in the phase diagram of PZT. We choose a solid solution of lead zirconate titanate, where on one side we have the lead zirconate and on the other side we have lead titanate. So as we can see that above the Curie temperature the PZT has no polarization and is a cubic structure. But as we take the PZT below the Curie temperature, there is a spontaneous polarization, hence causing the cubic PZT to elongate or distort and change to a tetragonal or rhombohedral shape. But still the structure is not so unstable that it cannot return back to the symmetrical cubic when the temperature increases. But if we take that tetragonal PZT and apply an electric field, that it forces the polarization to stay intact while it is still below the Curie temperature, and that will cause enough structural instability along this phase boundary called the morphotropic phase boundary, which is achieved at a eutectic composition of about 52% lead zirconate and 48% lead titanate, and as a result of which all the piezoelectric coefficients, the dielectric constants, becomes very large. Now, what is electric poling? The electric poling action implies the alignment of the dipoles present in the cubic system of the PZT when an electric field is applied and the temperature is raised above the Curie temperature. But why increasing the temperature is not enough? Why do we need to apply an electric field? The problem is that we cannot gain a good polarization even if the temperature of the crystal is above the Curie temperature, as these PZTs are polycrystallines, and unlike the single crystals, they can only align up to an extent within their domains. But if we pass an electric field or apply a voltage along with crossing the Curie temperature, it would force these unpoled or unpolarized dipoles to align in the direction of the electric field. And now the polarization in the material will stay the same even when the electric field is switched off. This action is called the electric poling. In this figure below, we have a piezoelectric disc. In figure B and C, there is a direct piezoelectric effect leading to the generation of electricity when the disc is compressed and hence has a generation action. And in figure D and E, as an electric potential is applied to the same material, it undergoes a mechanical strain that is a converse of the piezoelectric effect, and it is like a motor or mechanical action. Both the effects are extremely useful in a diverse range of applications. Specifically, the direct effect is used as a sensor and energy transducer, whereas the inverse effect is used as an actuator-based application. So there can be two types of piezoelectric responses. Hence we sometimes even call it a multiferroic, or more specifically a bidirectional transducer. Because of their and we call it because they convert mechanical energy to electrical energy and vice versa. Hence the PZT can function as a motor, a generator, and can even act as a sensor as well. This gives us the opportunity to discuss about their various applications. PZTs can be used as a sensor, where it can sense pressure, acceleration, and convert it into electrical signals. They can also be used as an actuator, where it can control precision movements. They can also be used as a transducer, in fact a bidirectional transducer, as it can convert one form of energy to another, and vice versa. As we can see, almost all of the engineering branches benefit from these piezoelectric smart materials. In fact, the most common use of PZTs can be found in common devices such as gas igniters, speakers, and buzzers. PZTs are used in sensing-based applications. They can detect even some of the most minor disturbances and anomalies, which make them ideal devices in industrial non-destructive testing and medical imaging. PZTs have a piezoelectric constant or sensitivity nearly 2 orders of magnitude higher than the natural single crystals, and can be produced by cheap sintering processes. And hence they can be used in applications like active health monitoring. By the word active health monitoring, here health, I mean health of structures like bridges, dams, trains, and so on. Since we generally use connectors such as bolts and nuts in construction bridges and trains, now these connection elements may lose or develop crack due to external impact caused due to movement of the locomotives. And if it is not monitored regularly, it may lead to unannounced and catastrophic disasters. Also, it's not feasible to monitor it manually every hour and so. So these piezoelectric sensors, which can produce reasonable accuracy and are suitable materials for structural restoration compared to other conventional materials here, as they are lightweight as well. Another application of sensors could be seen in active vibration damping. Smart structures that use different piezoelectric patches to control the vibration of thin plates have been of countable interest in recent years. Here, when the material is bent by a vibration in one direction as the train passes, the system responds to the bend and sends electric power to the piezoelectric element to bend it in the other direction. The idea is to detect the change in the vibration behavior of the entire wheel caused by surface rolling. A piezoelectric actuator features a very high strain output, a high response speed, and a high displacement control accuracy. All of these makes it advantageous for applications of high-tech equipment such as scanning tunnel microscopy (STM) and atomic force microscopy (AFM). These piezoelectric based actuators are also useful in implantable hearing aid. A PZT thin film microsensor and actuator are extremely useful here. One such application could be seen here. There is a tiny acoustic actuator that is fit into the cochlea, part of the inner ear, to generate significant acoustic stimulation as implantable hearing aid. Such actuators, when combined with shortened cochlear implant electrodes, have the advantage of better speech recognition in noisy environments. Other than that, we have the inkjet printers. The piezoelectric actuators in the printer head act as a small diaphragm, or otherwise change the geometry of an inkwell so that the ink drop are forced out of the orifice onto the paper drop by drop. PZTs in ultrasonic transducers. When on applying an oscillating voltage to these piezoelectric materials, they can cause it to squeeze at a certain frequency and can cause it to oscillate. And this is how ultrasound functions. So as the piezoelectric material vibrates at a certain frequency, it produces a sound wave. These sound waves then goes into the mother's womb and will hit the baby's organ and will bounce back. Now as these bounce back waves is received by another piezoelectric material PZT, that takes pressure, they basically takes the pressure waves and turn it into electrical signals, which then could be measured. Another common use of these PZTs could be found in speakers and buzzers. A buzzer is anything that produces sound. They are driven by an oscillating electronic circuit. A piezoelectric element may be driven by either an oscillating electronic circuit or another audio signal source, which is driven by a piezoelectric audio amplifier. Thank you everyone for listening to this presentation. I hope you enjoyed it.